Welcome to the Sleepy Scholar, where we explore fascinating topics in history, science, and engineering. Perfect to learn from as you drift off to sleep. Tonight, we'll be looking at a curious question. Why don't railroads need expansion joints when almost every road and bridge seems to? The answer takes us through the hidden design of steel rails, the challenges of heat and cold, and the clever engineering that keeps trains running smoothly. Before we begin, I'd love to hear your thoughts. Have you ever noticed the gaps in concrete highways, but wondered why train tracks don't have the same? Share your answer in the comments below. I'll be reading them. And if you enjoy learning while you relax, don't forget to gently tap the like button and subscribe so you don't miss the next journey into sleepy knowledge. Now let's settle in, take a deep breath, and discover the quiet secret of seamless railroads. Why railroads don't need expansion joints. If you've ever driven across a bridge or down a highway, you've probably noticed seams in the road. These little gaps are called expansion joints. They're there for a very practical reason. When the weather gets hot, the concrete or steel expands. When the weather turns cold, the material shrinks. Without those joints, the stress would build up and the structure could crack or buckle. So here's the question. If roads and bridges need expansion joints, why don't railroad tracks? Rails are made of steel, and steel expands quite a bit when it gets hot. On a sunny summer day, the surface of a rail can reach extremely high temperatures, and in winter, the same piece of steel might be freezing cold. That's a huge swing in temperature, which means the length of the rail is constantly trying to change. You'd expect the track to split apart or fold over itself, but it usually doesn't. A train can glide down a continuous rail at high speed without hitting bumps every few meters. This puzzle is interesting because it touches on something universal. All materials expand and contract. Engineers who design bridges, roads, pipelines, and railroads all face the same problem. But railroads deal with it differently. Instead of cutting in lots of gaps, modern railroads rely on special techniques that keep the rails safe, strong, and smooth without needing constant joints. In this essay, we're going to explore why railroads can work this way. To get there, we'll first need to talk about the basics of thermal expansion, what it is, how it works, and why it seems like rails should need expansion joints, just like roads do. Once we understand that, we'll move into the history of railroads, the development of modern welded track, and the clever tricks engineers used to keep those long steel rails in place through heat and cold. The short version is this: railroads don't ignore thermal expansion. They've learned to control it. And that choice, as we'll see, not only makes the tracks stronger, it makes train travel smoother and more efficient too. Thermal expansion basics. Let's start with the basics. Thermal expansion is just a fancy way of saying that things get bigger when they're hot and smaller when they're cold. This happens because of the way atoms behave. In a solid piece of material, the atoms are held together like tiny springs. When the material heats up, those atoms vibrate more. The vibrations push the atoms farther apart, which makes the whole object grow a little larger. When the material cools, the atoms slow down and come closer together, and the object shrinks. This isn't just theory, it's measurable. Engineers use something called the coefficient of thermal expansion to figure out how much a material changes size with each degree of temperature change. For steel, which is what rails are made of, the number is about 12 millionths per degree Celsius. That sounds incredibly small, but it adds up. Here's an example. Imagine a steel rail that's 1 kilometer long. That's about 2/3 of a mile. If the temperature of that rail goes up by 30 degrees Celsius, say, from a cool spring morning to a hot summer afternoon, that rail will try to get about 36 centimeters longer. That's more than a foot of extra length in just 1 kilometer of track. And of course, railways aren't just a kilometer long. They stretch for hundreds of kilometers. So the amount of expansion and contraction steel wants to do is very large. If that length change were left uncontrolled, the rails would push into each other in summer and leave dangerous gaps in winter. Now let's compare that to concrete, which is used in highways. Concrete also expands and contracts, though a little less than steel. But concrete roads are built in slabs. Each slab is rigid and can't really bend or stretch. That means every single section of road tries to move on its own when the temperature changes. If there's no room to move, the slabs crack. That's why roads and sidewalks have those little seams. You could think of them as controlled cracks. The seams give each section space to expand without breaking. Rails, at first glance, seem like they should need the same treatment. In fact, in the early days of railroads, they did. Rails were manufactured in short pieces, maybe 20 or 30 feet long. Each piece was joined to the next with a steel plate, leaving a tiny gap for expansion. That's where the classic clickety-clack sound of trains came from, the wheels hitting those joints one after another. But those joints came with problems. Every joint was a weak spot. Over time, the ends of the rails wore down and needed repairs. The ride was rougher, the noise was louder, and maintenance crews had to constantly check and replace the joints. Modern railroads solved this by flipping the problem around. Instead of letting every rail move on its own, they decided to weld rails together into much longer lengths. These continuous rails don't rely on expansion gaps. Instead, they spread the expansion and contraction forces along their entire length. The rails are anchored tightly to the ground using heavy ties, clips, and rock ballast. This holds them in place so they don't move freely. You might wonder, doesn't that mean the rails are just being squeezed really hard in the summer and stretched in the winter? The answer is yes, and that's the key difference. Concrete can't handle that kind of stress, it cracks. Steel, on the other hand, is incredibly strong. It can absorb huge amounts of compressive or tensile stress without failing. So instead of moving, the rail just carries that stress safely inside it. Think of it this way. Imagine a strong rubber band stretched between two walls. As the room warms up, the band wants to get longer, but the walls hold it in place. The result is tension in the band. As the room cools, the band wants to shrink, but again the walls resist. So now it's in compression. As long as the band is strong enough, it can handle those forces without snapping. That's what steel rails do. Of course, engineers don't leave this to chance. They install rails at a neutral temperature, a middle point where the rail is neither stretched nor compressed too much. That way, in summer heat, the stress isn't unbearable, and in winter cold, it's still within safe limits. Maintenance crews also check rails regularly and sometimes distress them by adjusting their length. So the reason railroads don't need expansion joints is not because thermal expansion doesn't happen. It absolutely does. The reason is that steel rails, when welded into long continuous lengths and held firmly in place, can carry those stresses safely. Instead of lots of little joints, the entire rail works as one strong, continuous member. And that's the big difference between roads and rails. Roads are built from short, stiff slabs that need room to move separately. Rails are built as continuous, flexible members that can absorb and distribute the stress of expansion without cracking apart. With that foundation in mind, we can now move to the history of railroads, the problems with early jointed track, and the engineering advances that gave us the smooth, quiet, continuous welded rail we see today. Historical background of rail expansion. To understand why modern railroads don't use expansion joints, it helps to step back in time and look at how railways started. The story begins in the early 1800s, during the very first days of railway construction in Britain. Back then, engineers faced the same problem we've been talking about. Steel expands and contracts with temperature. But their solution looked very different from the tracks we know today. Early railways and short rails. When the first railways were built, steelmaking wasn't as advanced as it is now. Rails could only be manufactured in short lengths, usually about 15 to 30 feet long. These short rails were laid end to end, and the ends were joined with a simple metal plate called a fish plate. A pair of bolts held the plates together, keeping the rails aligned so train wheels could pass smoothly across the joint. But those joints weren't welded, and they weren't tight. A small gap was left between each pair of rails to give them room to expand and contract with the seasons. If you've ever heard the sound of an old train clickety-clack, that rhythm came from the wheels striking those gaps one after another. Every few seconds, another joint passed under the train. This design worked reasonably well at first. The small gaps acted like miniature expansion joints. Each rail was free to stretch or shrink a little bit without causing much trouble. And because the rails were short, the total expansion in each piece wasn't that large. The downsides of joints. But while expansion was managed, the joints created a new set of problems. For one, the ride wasn't smooth. Every time a wheel crossed a joint, it made a noise and a bump. Early passengers often complained about the rough, noisy ride. More seriously, the joints were weak points. The ends of the rails carried much more stress than the middle sections. As heavy locomotives rolled over them, the ends would pound against each other, slowly wearing down the metal. This led to cracks, chips, and gaps. Maintenance crews had to constantly inspect the joints, tighten the bolts, and replace worn-out rails. In fact, by the late 1800s, railroads discovered that joints were responsible for the majority of track problems. They made up only a tiny percentage of the rail's total length, but they caused most of the failures. One popular saying among railroad workers was that a track is only as strong as its joints. The problem only got worse as trains became faster and heavier. In the early days, trains moved at perhaps 20 or 30 miles an hour. By the late 19th century, passenger trains were running at 60 miles an hour or more, and locomotives were several times heavier. At those speeds and weights, the pounding on every joint grew more destructive. Railroads began searching for ways to reduce or eliminate the joints altogether. Early experiments with welding. At the turn of the 20th century, steelmaking improved, and rails could be rolled in longer lengths. Instead of 30-foot rails, manufacturers could produce rails 60 feet long or even longer. This reduced the number of joints, but it didn't solve the problem completely. Engineers also began experimenting with welding rails together. At first, welding technology wasn't advanced enough to make reliable, strong welds over long lengths. But over time, methods improved. By the 1920s and 1930s, railroads started laying welded track in test sections. Instead of many short rails, these were joined into lengths hundreds of feet long. The results were promising. Welded rails gave a smoother ride and needed less maintenance. But one major obstacle remained: thermal expansion. How could engineers weld rails together into very long lengths without leaving gaps for the metal to expand? Wouldn't the rails just buckle in the summer heat? The birth of continuous welded rail. The breakthrough came with a deeper understanding of how steel rails behave under stress. Engineers realized that if the rails were held firmly in place, fastened to wooden ties or concrete sleepers, anchored in heavy rock ballast, and installed at a neutral temperature, they could absorb the stresses of expansion without actually moving much. This idea led to the development of what we now call continuous welded rail, or CWR. Instead of leaving small gaps every few meters, railroads began welding rails into quarter-mile lengths, and sometimes even longer. These long sections were laid in place, carefully stressed, so that they were stable at typical regional temperatures. In North America, continuous welded rail began spreading in the 1950s. By the 1970s, it was becoming the standard. In Europe and Japan, The adoption was even quicker, especially on high-speed lines. Today, most mainline tracks around the world use CWR. The old jointed track still exists in some yards, sidings, and low-traffic lines. But on busy railways, the clickety-clack of joints has almost entirely disappeared. Benefits of continuous welded rail. The switch to welded rail transformed railroading. For passengers, the difference was immediately noticeable. Trains became quieter and smoother. Instead of the constant bumping over joints, they seemed to glide. For freight, welded rails allowed heavier loads to be carried with less wear and tear. For the railroads themselves, the biggest benefit was maintenance. Joints had been the #1 source of trouble. With welded rail, that problem nearly vanished. The track became stronger, more stable, and longer lasting. Although continuous welded rail required new techniques to handle thermal stress, the overall cost savings and performance improvements made it well worth the investment. Special cases. It's worth noting that expansion joints haven't vanished completely from railroads. They're still used in special situations, like where a track crosses a large bridge, or in regions with extreme temperature swings. In these cases, engineers may install devices called rail expansion joints that look a little like giant sliding puzzle pieces. These allow the rail to expand and contract without breaking alignment. But on ordinary ground, continuous welded rail is now the norm. Wrapping up the background, so the history of railroads shows a clear progression. At first, short rails and joints were the only option. Those joints acted like expansion gaps, but they created endless headaches for maintenance crews. As steelmaking improved, rails got longer, and welding made it possible to create continuous lengths. Once engineers figured out how to manage thermal stress across those long rails, the age of jointed track was largely over. The historical background teaches us two things. First, expansion is a real issue that railroads have always had to face. And second, the way railroads solved the problem wasn't by copying roads and adding more joints. Instead, they moved in the opposite direction toward fewer joints, longer rails, and stronger continuous track. In the next section, we'll dig deeper into continuous welded rail itself, how it works, why it doesn't buckle under stress, and what makes it such a reliable solution for modern trains. Continuous welded rail and its advantages. By the middle of the 20th century, the railroad industry was standing at a crossroads. The old way of doing things, short rails joined together every few meters, was showing its age. Maintenance costs were high, the ride was rough, and the familiar clickety-clack of joints wasn't just charming background noise, it was a sign of weakness. Railroads wanted something smoother, stronger, and more modern. The solution was continuous welded rail, usually called CWR. Today, it's the standard on almost every busy rail line in the world. But what exactly is continuous welded rail? And why is it so much better than jointed track? To answer that, let's step back and picture the difference. The clickety-clack era. Imagine riding a passenger train in the 1930s. You sit down by the window as the locomotive lurches forward. Almost immediately, you hear it. Clickety-clack, clickety-clack. The sound has a rhythm, like a metronome. Every few seconds, another set of wheels hits a joint between rails. At first, it might feel cozy or nostalgic, but after a while, you notice the bumps. Your teacup rattles on the saucer. The car sways slightly every time a wheel crosses a gap. For passengers, it's not exactly uncomfortable, but it's not smooth either. Now imagine you're a railroad worker. Every one of those joints is a weak point. Bolts come loose, plates crack, and gaps widen. Crews are constantly out on the line tightening, replacing, and patching. The track is more joints than rails. It works, but it's exhausting. That was the old world, the idea of continuous rail. The dream was simple. What if the rails could just be one long piece, stretching for miles, with no joints at all? The ride would be smooth, the noise would vanish, and the weak spots would disappear. But making that dream a reality wasn't simple at all. Steel rails are heavy and stiff. A single length 60 feet long already weighs hundreds of pounds. Making rails hundreds of meters long was impossible in the factory. So instead, engineers began experimenting with welding shorter rails together. At first, this was done in special welding plants. Short rails were lined up end to end, their ends heated until they were glowing, and then pressed together to fuse into one. Over and over, until the rail was hundreds of meters long. These welded lengths were then transported to the railway and laid down like giant steel ribbons. The first time a train rolled down welded rail, the difference was clear. The bumps were gone. The clickety-clack was gone. It was like riding on glass. How long is continuous? When people hear the phrase, continuous welded rail, they sometimes imagine a single piece of steel stretching from coast to coast. That's not quite true. Rails are welded into lengths that are often a quarter-mile long, sometimes longer. These long sections are then connected together with very few joints, sometimes using special welded joints, sometimes with heavy-duty connectors. In practice, CWR makes the track feel continuous. The number of joints drops from hundreds per mile to just a handful. For a passenger, the difference is night and day. For the railroad company, it's even more important. The advantages of CWR. So what are the real advantages of continuous welded rail? Let's look at them one by one in plain language. 1. A smoother ride. The most obvious benefit is comfort. Without joints, trains glide instead of bump. The cars sway less, drinks don't rattle, and passengers can read, write, or nap without interruption. For freight trains, it means less jostling of cargo. Imagine shipping a load of delicate glassware or electronics. On jointed track, Every bump risks damage. On welded track, the journey is gentler. Even for bulk freight coal, grain, oil, the smoother ride reduces wear on the cars themselves. 2. Less noise. The romantic sound of clickety-clack is nice in an old movie, but for people living near railways, it was constant noise. Every train brought minutes of clatter as wheels pounded joints. Continuous welded rail makes modern railways much quieter. Trains still make sound, of course, the hum of steel on steel, the rush of air, but it's smoother, less jarring. For high-speed rail in particular, this is critical. A train moving at 200 miles per hour couldn't possibly handle the pounding of joints every few seconds. Welded rails make high-speed travel possible. 3. Stronger track. Joints were the weak spots of the old system. They wore down quickly, broke often, and caused many derailments. With CWR, those weak spots are almost entirely gone. The track is stronger, more stable, and less likely to fail suddenly. Think of it like a chain. If the chain has 100 links and one link is weak, the chain will break there. By removing the weak links, the whole chain is stronger. 4. Less maintenance. For the railroads themselves, this might be the biggest advantage. With jointed track, maintenance crews were constantly busy. Bolts needed tightening, plates needed replacing, and damaged joints had to be fixed. It was expensive, time-consuming work. With CWR, the number of joints drops dramatically, which means maintenance needs plummet. Crews still inspect and care for the rails, but the constant grind of fixing joints is gone. Over the long term, this saves huge amounts of money. 5. Higher speeds and heavier loads. Because welded rail is stronger and smoother, trains can safely go faster. High-speed rail wouldn't even be possible without it. But even ordinary freight trains benefit. Heavier loads can be carried without fear of pounding the track to pieces. This is part of why railroads became more efficient in the second half of the 20th century. Longer trains, heavier cars, and higher speeds were possible because the track itself was better. The challenges of CWR. Of course, continuous welded rail isn't magic. It brought its own set of challenges. The biggest one, as we've already discussed, is thermal expansion. With no gaps to expand into, the rails build up stress. In summer, they're under compression, wanting to get longer. In winter, they're under tension, wanting to get shorter. If the stress gets too high, the rail can buckle sideways into what's called a sun kink. These kinks are rare but dangerous. Railroads learned to manage this by installing rails at a neutral temperature, usually somewhere in the middle of the local climate range. They also anchor the rails very firmly with ties, clips, and ballast, so the steel is held in place. Crews check the rails regularly, and if needed, they distress them, basically adjusting the rail so it's not carrying too much stress. So while CWR has many advantages, it also requires careful management. It's a balance, smooth, strong track, but with extra responsibility to monitor it, changing the feel of railroads. One interesting effect of continuous welded rail is how it changed the experience of rail travel. For more than a century, the sound of clickety-clack defined train rides. It was part of the atmosphere, part of the romance of railroads. Writers mentioned it in poems, musicians imitated it in songs, and travelers associated it with long journeys across the countryside. When CWR spread, that sound disappeared almost overnight. Suddenly, train rides were quiet. Some passengers missed the old rhythm, but most quickly realized the trade was worth it. Smoother, faster, quieter rides. For railroad workers, the change was even bigger. Maintenance crews, once overwhelmed by joints, found their work shifting toward new tasks. Instead of tightening bolts day and night, they monitored rail stress and managed welded track. The nature of track work changed, but the workload became more manageable. High-speed rail and CWR. Nowhere is the importance of continuous welded rail clearer than in high-speed rail systems. The famous Shinkansen in Japan, the TGV in France, and other bullet trains rely completely on welded rails. At speeds over 180 miles per hour, even the tiniest bump can be a major problem. Joints would make such speeds impossible. Instead, these lines are built with long, smooth, welded rails that allow trains to fly across the landscape with barely a ripple. The comfort, safety, and speed of high-speed rail all depend on the strength and smoothness of CWR. Everyday railroads too. But continuous welded rail isn't just for high-speed trains. It's used almost everywhere now. In North America, freight railroads covering thousands of miles have switched to CWR. Even on slow branch lines, the benefits are clear. The result is that trains today, whether they're carrying passengers, coal, cars, or grain, run on smoother, quieter, stronger track than ever before. Wrapping up this section, so what makes continuous welded rail so important? In short, it solved the biggest weakness of old-fashioned tracks. It gave trains a smoother ride, reduced noise, eliminated weak spots, lowered maintenance, and made higher speeds possible. It didn't erase the problem of thermal expansion, but it changed how railroads deal with it. Instead of relying on lots of little joints, they built rails that carry the stress themselves, anchored solidly in place. The change was revolutionary. Railroads went from being defined by the sound of joints to being defined by their absence. And in doing so, they became more efficient, more comfortable, and more capable than ever before. In the next part of this essay, we'll look more closely at the engineering solutions railroads use to control expansion in welded rails, how they choose neutral temperatures, how they anchor rails to ties, and what they do when stress builds too high. Continuous welded rail, CWR, and its advantages. If you've ever ridden a train, especially in modern times, you might have noticed something that feels almost magical compared to the trains of old. The ride is smooth, steady, and much quieter than people often imagine when they picture trains. What happened to the famous clickety-clack sound, where every wheel that passed made a rhythmic noise at each joint in the rail? Why do modern trains feel like they glide instead of bumping along? The answer lies in one of the biggest breakthroughs in railroad history: continuous welded rail, often shortened to CWR. This invention completely changed how railroads are built and maintained, and it's one of the main reasons railroads don't need those obvious expansion joints that you see in roads or bridges. To really understand why, let's walk through what CWR is, why it was invented, and the big advantages it brings. The problem with old rail joints: back in the early days of railroads, the technology was simple. Rails came in short pieces, maybe 30 feet long, sometimes a little more, sometimes a little less. These pieces were bolted together end to end with a connector called a fish plate, creating what was known as jointed track. At first, this made sense. Manufacturing very long pieces of steel was difficult, and transporting them even more so. Cutting rails into shorter lengths made it easier to make, move, and install them. But these joints caused all sorts of problems. Noise, that famous clickety-clack, wasn't just charming. It was actually the sound of wheels bouncing slightly over every gap between rail sections. It was a constant reminder that the track wasn't truly smooth. Wear and tear. Every time a train wheel hit a joint, it caused stress on the rail, the wheels, and the underlying support. Over time, these little impacts added up, creating weak points that required frequent repairs. Maintenance headaches. Crews had to constantly inspect and replace joints, tighten bolts, and check alignment. A huge amount of railroad labor was tied up just in dealing with these spots. Speed limits. Joints were weak points. Trains had to run slower in many places because the constant bumping made it unsafe to go too fast. So while jointed track worked for the time, it wasn't an ideal long-term solution. The big idea: welding rails together. Engineers began asking, what if we could just eliminate the joints altogether? Instead of 100 short pieces bolted end to end, what if we made one long, seamless stretch of steel? That's where the concept of welding came in. By using heat and pressure, steel rails could be fused together to create one continuous piece. No bolts, no gaps, no clickety-clack. At first, this was done in smaller stretches. A few pieces would be welded together into something maybe 300 or 400 feet long. But as techniques improved, those welded strings got longer and longer, thousands of feet in length, sometimes even a full quarter of a mile in one go. Eventually, entire rail lines could be built with rail that seemed endless, stretching out like a ribbon of steel with no joints in sight. This new approach became known as continuous welded rail. And while it might sound like just a simple upgrade, swapping short rails for long ones, it actually solved a mountain of problems at once. A smoother, quieter ride. The most obvious change people noticed was the way trains rode on welded rail. Without the gaps between each piece, the train wheels rolled silently and smoothly. That rhythmic clickety-clack sound became rare. In fact, many people who grew up riding older trains still miss the sound because it had a kind of nostalgic charm. But for railroads, passengers, and freight companies, losing that noise was a blessing. It meant less shaking, less bumping, and less stress on the equipment. If you've ever taken a modern train and been surprised at how gentle it feels compared to what you imagined, you can thank continuous welded rail. Less maintenance, more reliability. Another huge advantage of welded rail was maintenance, or rather, the lack of it. Remember how crews used to spend endless hours checking bolts, tightening plates, and fixing gaps. With CWR, all of that basically disappeared. Fewer joints meant fewer weak spots. Instead of hundreds of little places where the track could fail, you had one strong, continuous line of steel. That saved railroads enormous amounts of time and money. And because the rails stayed stronger for longer, trains could run more reliably. There were fewer breakdowns, fewer emergency repairs, and fewer delays caused by track problems. Higher speeds and heavier loads. Railroads exist to move things quickly and efficiently. But jointed track had a natural speed limit because hitting those joints over and over again wasn't safe at high speeds. Once welded rail came along, that barrier disappeared. Suddenly, trains could run faster without worrying about constant bumps. Passenger trains became smoother and quicker. Freight trains could carry heavier loads without shaking the track apart. This was especially important for high-speed rail systems. Think of the famous bullet trains in Japan or France. Without welded rail, those speeds would be impossible. The trains simply couldn't stay stable on jointed track. Continuous welded rail made the dream of truly high-speed trains a reality, handling thermal expansion differently. Here, where welded rail really ties into our big question about expansion joints. You might be thinking, wait a second, if the rail is one long piece of steel, doesn't that make the expansion problem worse? After all, the longer the steel, the more it expands when it gets hot. And you're right, it does expand more. But here's the clever part. Instead of leaving little joints everywhere to handle that expansion, railroads manage it in a completely different way. When continuous welded rail is installed, it's usually laid down and anchored at a specific temperature, called the rail's neutral temperature. This is a sort of sweet spot, often chosen to be the average temperature for that region. At this temperature, the rail is neither stretched nor compressed, it's just right. Then, when the weather gets hotter or colder, The rail does want to expand or shrink, but because it's tightly fastened to the ties and surrounded by heavy stone ballast, most of that force is held in place. Instead of the rail freely sliding around, the stress gets spread out across thousands of feet. It's like holding a long rubber band tightly in place. It may pull and push a little, but it stays put. Yes, in extreme cases, railroads do have to watch out for buckling, called a sun kink. But with proper installation and monitoring, welded rail is far more stable than jointed track ever was. We'll dig more into that in later sections, but for now, the key idea is this. Welded rail handles thermal expansion not by leaving gaps, but by locking the rail into position and controlling the stresses. The big advantages at a glance. To sum up, here are the main reasons continuous welded rail was such a game changer. 1. Smooth ride. No more bumping over joints. Passengers and cargo both travel more comfortably. 2. Less noise. Goodbye to the constant clickety-clack. Hello to a quieter journey. 3. Reduced maintenance. Fewer joints to inspect and repair. Saves railroads massive costs. 4. Greater safety. Fewer weak points mean fewer accidents caused by joint failures. 5. Higher speeds. Welded rail allows trains to travel much faster, especially modern high-speed trains. 6. Stronger over time. Long stretches of steel distribute stress more evenly than many short pieces. A quiet revolution. What's amazing about continuous welded rail is how quietly it transformed railroads. There wasn't a big, flashy moment where everything changed overnight. Instead, as railroads replaced older jointed track with welded rail, things just steadily got better. Smoother rides, fewer delays, faster speeds. Today, if you ride a train almost anywhere in the world, chances are you're on welded rail. Jointed track still exists here and there, often in older sidings or less busy branch lines. But the main lines, the ones carrying heavy freight and fast passenger trains, are almost entirely continuous welded rail. It's such a standard now that most people don't even realize how different things used to be. The clickety-clack is now mostly a sound effect for movies or a memory for older generations. And while the idea of welding rails together might seem simple in hindsight, it took decades of innovation, trial, and error to make it practical on a large scale. But once it became widespread, it reshaped railroads forever. Why it matters to our big question. So why spend so much time talking about continuous welded rail in a discussion about expansion joints? Because CWR is the heart of the answer. With jointed track, expansion joints were everywhere by default. Every single connection was basically a mini expansion joint. That caused all sorts of problems. But with welded rail, the need for those joints largely disappeared. Instead, engineers figured out how to manage expansion in a smarter way by anchoring, stressing, and maintaining the rail as one continuous piece. It might sound counterintuitive, but in the end, making the rail longer actually solved the problems that shorter rails created. Instead of hundreds of little weak points, railroads now had one strong, unified track that could handle the stresses of temperature without breaking apart. That's the story of continuous welded rail, a quiet but powerful revolution that changed railroads forever. It didn't just eliminate the clickety-clack, it also eliminated the need for those constant expansion joints, paving the way for the safe, smooth, and speedy trains we know today. Roads versus rails. Why they handle heat so differently. When you look at a road and a railroad side by side, they almost seem like cousins. Both stretch off into the distance, carrying people and goods from one place to another. Both are exposed to the same weather, the same heat from the summer sun, and the same cold of winter nights. And both are built from materials that expand and contract when the temperature changes. But when you drive along a highway, you'll see and feel little seams in the pavement. Those are expansion joints, gaps built in on purpose to let the road slabs shift a little without breaking. On the other hand, when you look at railroad tracks, you won't see those regular gaps. The rails seem continuous, like one long piece of steel stretching endlessly forward. So why the difference? If both roads and rails deal with the same heat, why do roads need joints and rails usually do? Let's dive in and look at the differences, not just in material, but in how each structure works. Concrete slabs versus continuous rails. Let's start with roads. Most major highways are made of concrete slabs. Picture a giant sheet of sidewalk, but instead of being for pedestrians, it's built for trucks going 100 kilometers per hour. These slabs are laid side by side, kind of like tiles on a floor. Now, here's the problem. Each slab of concrete is its own piece. When the sun bakes it, the slab wants to expand in every direction. When it gets cold, the slab shrinks. But because the slab can't move freely, it's locked in by the other slabs beside it, by the ground underneath, and by curbs or barriers at the edges. The only way it can deal with that stress is by cracking. Cracking isn't good if you're trying to build a smooth, safe road. So engineers give the slabs a little help. They cut or build in expansion joints. These are gaps, often filled with flexible material, that let the slabs push against each other without shattering. Now compare that to railroad tracks. Rails are long, narrow pieces of steel joined together into what's called continuous welded rail. Instead of acting like independent slabs, they're more like a long rope stretched tight. The rail can expand or contract, but because it's anchored down and supported along its entire length, the forces are spread out. The stress doesn't build up in just one spot like it does with concrete slabs. It's the difference between lots of little puzzle pieces that each want to move on their own, and one big, continuous strip that shares the movement evenly. The nature of the materials. The materials themselves also play a role. Concrete is strong when you press down on it. That's why it's great for supporting heavy vehicles. But it's brittle when it comes to pulling or stretching forces. If you try to bend or stretch concrete, it cracks easily. That's why even sidewalks have those little cut lines called control joints to tell the concrete where it's allowed to crack. Steel, on the other hand, is flexible compared to concrete. It can handle stretching, compressing, and bending much better. A steel rail can bow slightly, take on stress, and still hold its shape. That makes steel naturally more forgiving when it expands and contracts with temperature. So while concrete needs those obvious expansion joints to protect itself, steel rails can rely more on their strength and the way they're held in place. How stress is spread. Another way to think about it is this: where does the stress go? On a road, each concrete slab is basically on its own. When it gets hot, that single slab expands. When it cools, it contracts. The stress builds up right inside the slab, and without joints, it will crack. On a railroad, the rails are tied down to wooden or concrete ties, which are themselves held in place by the rock bed underneath, called ballast. Each tie, each clip, each rock helps resist the movement. Instead of one piece taking all the stress, the forces are distributed across hundreds of meters of track. It's kind of like trying to push against a single brick versus trying to push against a whole brick wall. The wall resists better because the force spreads out. That's how rails work. They spread the expansion and contraction forces along the line, rather than concentrating it in one place. Why roads can't be continuous? You might wonder. If rails can be welded together into one continuous strip, why don't we just make roads continuous too? Why not pour one giant road with no joints at all? The answer goes back to material and practicality. Concrete doesn't handle tension well, and even with reinforcing steel bars inside, called rebar, a giant continuous slab would still crack under temperature changes. Plus, the logistics of pouring a single continuous highway are nearly impossible. You'd need massive amounts of material all at once, with no chance to stop and adjust. With rails, welding long sections together is much more manageable. Steel can be heated, stretched, and joined without losing its properties. The technology is well established and practical. For concrete, though, expansion joints remain the simplest, cheapest, and most reliable solution. The ride experience. If you've ever driven on a highway and felt that rhythmic thump, thump, thump as your car goes over joints, you've experienced expansion joints directly. It's not always pleasant, especially on older roads where the joints aren't perfectly smooth anymore. Compare that to riding a train. Modern trains glide along the track with hardly any noticeable bumps. In the old days of jointed rail, passengers heard and felt the clickety-clack of wheels crossing gaps. But continuous welded rail eliminated that, making train rides quieter and smoother. So the absence of expansion joints in railroads isn't just an engineering choice. It actually makes the travel experience better too. What happens when rails do buckle? Of course, none of this means that rails are immune to problems. When rails get extremely hot, they can still buckle, creating dangerous bends known as sun kinks. These are rare, but they do happen if the rail wasn't installed or maintained correctly. When roads face heat stress, they might crack between joints or push up slightly, but usually in a way that vehicles can still pass, at least temporarily. When rails buckle, however, trains can derail. That's why railroads put so much effort into preventing buckling in the first place, through anchoring, monitoring, and maintenance. So in a way, roads accept that their slabs will move and build joints to allow it. Railroads, on the other hand, put in the work to make the rails act as one long, stable piece that can handle the stress without visible joints. Everyday examples. If you want to picture the difference in everyday life, think of two things. A tiled kitchen floor. Each tile expands and contracts on its own. If you didn't leave tiny gaps filled with grout, the tiles would push against each other and crack. That's how roads work. A metal tape measure. It's one continuous strip of steel. When it's hot, it might expand a little, but the whole strip lengthens together. That's how rails work. A matter of design philosophy. At the end of the day, the difference between roads and rails isn't just material or method, it's philosophy. Roads are designed to be modular. Lots of pieces joined together, each allowed to move a little. Rails are designed to be continuous. One long piece that resists movement as a whole. Both solutions make sense for their context. Roads need flexibility because they cover wide areas, handle different vehicle types, and are made of concrete that doesn't like tension. Rails need continuity because trains depend on smooth, uninterrupted paths to stay safe and efficient. Wrapping it up. So why do roads need expansion joints, while rails usually do? Roads are built from concrete slabs that crack without joints. Rails are continuous steel strips that share stresses along their length. Concrete is brittle and needs space to move. Steel is flexible and anchored down. Roads accept movement by breaking the structure into smaller pieces. Rails fight movement by making the structure continuous and strong. It's two different answers to the same problem. How to deal with the fact that everything expands and contracts with temperature. And while both approaches work, it's railroads that give us that smooth, seamless ride without the thump-thump of expansion joints under our wheels. Safety and maintenance. Let's be honest. While modern railroad design has largely solved the problem of expansion joints, it doesn't mean railroads are completely immune to the forces of heat and cold. Steel is steel, and it still wants to expand when the sun beats down or contract when a winter storm blows through. The trick is that railroads have figured out how to manage that movement safely. This is where the story of safety and maintenance really comes into play. Imagine a hot summer day in the middle of July. The sun has been pounding down for hours, the rails are gleaming, and their surface is hot enough to fry an egg. The steel inside those tracks is expanding. If it pushes too far without enough resistance, something called a sun kink can occur. That's when the rail bows outward, almost like a snake wriggling across the ground. To a train, this is dangerous. If a train hits a sun kink at high speed, it could derail. Now, railroads know this, and they prepare for it. The first line of defense is in the installation process itself. When rail is laid, it's not just dropped onto the ground at any old time of year. Railroads aim to install continuous welded rail at what's called the neutral temperature, a middle ground where the rail is neither at its hottest nor its coldest. For many railways, this might be somewhere between 85 and 95 degrees Fahrenheit, around 30 to 35 Celsius. By locking the rail in place at that temperature, the engineers ensure that it can expand in the summer and contract in the winter without moving too far in either direction. But even with careful installation, railroads can't rely on luck. Track inspectors play a huge role in keeping things safe. You've probably seen those small high-rail trucks that ride along the tracks, or workers walking slowly down a stretch of line. They're checking for any signs of trouble, shifted ballast, loose fasteners, or bends in the steel that might signal a kink. These inspections happen constantly, especially during periods of extreme heat. Technology is also stepping in to lend a hand. Some railroads use rail temperature sensors that track the exact conditions on a piece of track in real time. If a rail gets dangerously hot, dispatchers might issue a slow order, which means trains have to crawl through that area at reduced speed. It's a bit inconvenient, but it keeps everyone safe while the risk of buckling is high. Another big part of safety is distressing the rail. Over time, steel can slowly build up hidden stresses inside it, especially if temperatures swing wildly from season to season. To fix this, maintenance crews sometimes cut a section of rail, let it expand or contract naturally, and then weld it back together at the proper neutral temperature. It's like resetting the tension on a guitar string so it doesn't snap. Of course, heat isn't the only challenge. Cold weather can also cause problems. When rails shrink in the winter, the stress pulls inward. In extreme cold, this tension can cause a rail to crack or even snap in two. That's why in northern regions, railroads have teams on standby during cold snaps to quickly repair broken rails. They bring in pre-welded replacement segments, slide them into place, and weld them so trains can keep running. The important thing to remember is that railroads accept expansion and contraction as facts of life. They don't fight against them with joints anymore. Instead, they monitor, plan, and adjust. Compared to roads, where cracks, potholes, and broken expansion joints are constantly forming, railroads have built a system of ongoing care that keeps the track in shape. This constant vigilance may sound exhausting, but it's what makes rail travel one of the safest forms of land transportation. Trains carry massive amounts of weight at high speeds, yet derailments caused by heat kinks or broken rails are relatively rare because the industry has developed these layers of defense. Future directions. Now that we've walked through how railroads currently handle the problem, it's worth looking ahead. Technology never stands still, and the rail industry is no exception. Even though railroads don't need traditional expansion joints anymore, they're still exploring future directions to make tracks safer, smarter, and easier to maintain. One of the most exciting areas is smart monitoring. Instead of relying only on human inspectors walking the line or riding in trucks, new systems use sensors embedded in the track itself. These sensors can measure temperature, stress, vibration, and even the presence of microcracks long before they turn into real problems. They can then send this information instantly to a control center. Imagine a dispatcher being able to see, in real time, which sections of track are heating up too quickly on a hot summer day. That kind of information allows railroads to act early, slowing trains or scheduling maintenance before anything dangerous happens. There's also work being done on material science. Steel has served railroads well for almost 2 centuries, but researchers are experimenting with new alloys that resist heat expansion more effectively, or that are less brittle in cold weather. Some companies are even investigating whether composite materials could play a role in the future. Although steel remains the king for now because of its unmatched strength and durability. High-speed rail, which is growing in many parts of the world, also pushes innovation forward. Trains traveling at 200 miles per hour demand tracks that are absolutely flawless. This means railroads are looking for tighter tolerances and better ways to manage stress, so there's no risk of even minor buckling. Japan's Shinkansen and Europe's TGV systems, for example, have led to advances in how rails are anchored and how ballast is maintained. As more countries invest in high-speed lines, these techniques will spread further. Finally, the future is likely to bring more automation in track maintenance. Robots and specialized machines are being designed to grind, weld, and adjust rails automatically, often working overnight when trains aren't running. This reduces human risk and ensures that maintenance can happen more regularly without interrupting schedules. In short, while the basic principle of continuous welded rail isn't going anywhere, the way we monitor and care for it is becoming increasingly sophisticated. The goal is always the same: smoother rides, safer trains, and fewer surprises from the forces of nature. Conclusion. So let's bring this story full circle. We started with a simple question: why don't railroads need expansion joints when roads do? At first, it seems like they should after all. Steel expands and contracts just like concrete or asphalt. But as we've seen, the story of the railroad is one of clever engineering and continuous adaptation. In the early days, railroads did use joints. Trains clattered over them, and maintenance crews spent endless hours fixing them. But with the invention of continuous welded rail, the game changed. Instead of treating expansion as a problem to be solved with gaps, railroads learned to manage it across long, seamless stretches of steel. The key is balance, installing the rails at a neutral temperature, anchoring them firmly with ballast and fasteners, and maintaining them with regular inspections and distressing. When the weather swings to extremes, railroads don't panic, they adjust. Whether that means issuing slow orders during heat waves or replacing broken rails in the cold. Compared to roads, which must rely on expansion joints and still crack and crumble under stress, railroads have developed a more elegant and durable approach. And as technology advances, with smart sensors, better materials, and automated maintenance, that approach is only getting stronger. The next time you're near a set of tracks, take a moment to think about what you don't see. You won't spot expansion joints every few feet the way you do with sidewalks or highways. Instead, you'll see long, smooth ribbons of steel stretching into the distance. Those rails are quietly carrying the weight of trains, the burden of heat and cold, and the pressure of time itself, all thanks to the ingenuity of generations of engineers and workers. So the answer is simple, but also profound. Railroads don't need expansion joints because they found a better way. And that's the story of why railroads don't need expansion joints. A small detail, but one that shows just how much thought goes into the world around us. If you enjoyed this quiet dive into hidden engineering, I'd love to hear from you. Was there anything in this story that surprised you? Leave a comment. If you'd like more relaxing lessons like this, gently press the like button and subscribe so you'll be here for the next one. For now, I hope this helped you unwind. Sleep well, and I'll see you in the next video.